You know, one of the hardest things I'm actually tasked with is taking abstruse field theory and using commonplace analogies. Some of the analogies really aren't all that commonplace. Now, I'm going to give you a relationship between conventional theories on electromagnetism and what we know about from a magnet, because I've even got questions from people that have bought really powerful magnets. So before we get onto the magnet in explaining field theory as opposite to magnetism and Gaussian flux, how could a really strong magnet have a really small field? Well, a more powerful magnet should have a big field around it, right? Because that makes more sense. You know, conventional logic tells us that if we have a larger box, we can fit more stuff in it, right? Can't fit too much in a jewelry box, right? But you can fit a lot of stuff in a really big trunk. Well, field theory works the opposite way. What we understand about field theory, at least human beings, requires a primer. Now, the primer is what I'm actually spelling out in the 4th edition of Uncovering the Missing Secrets of Magnetism. Uncovering the Missing Secrets of Magnetism, 4th edition, which is a free book, by the way. The 3rd edition is free on archive.org. Always has been free, always will be free. So, before we get to explaining the question I kept getting about magnets, let's first take a look at electromagnetism, whether it's light, or gamma, or ultraviolet. Let's just say we have here on the bottom, we have gamma. However, for it to be gamma, it actually have to be a lot tighter than that. Now, we can all agree that this spatial volume is a lot less than this spatial volume, right? Let's just say this is infrared, and this is UV. That would actually be a closer analogy as far as the diagram. Now, you think, well, up here we have some transverse electrical and magnetic. And down here we'd have magnetic and electrical. Same thing here with UV, E and M. Okay, so what about this spatial volume right here as opposed to this? Now, UV is a lot more powerful. And what is it? What's the formula? Energy equals Planck's constant times the frequency, right? Right. I didn't have that math formula pulled up directly in my head. So, what about the spatial volume that we have here between the two? Well, UV is a lot more powerful. So is X-ray. So is gamma. If I were actually to try to draw out gamma radiation, which I couldn't, which has an extremely high EV, it would be so tiny as that I couldn't actually draw it. It would be, by scale, it would be infinitely less than this. So, smaller the space, here's a primer. Smaller the space, the higher capacitance. So, as this gets smaller, energy goes up, right? And in this case, it would be energy's down compared to gamma or X-ray. This would be a lot less energetic UV radiation as opposed to infrared. So we get infrared, UV, gamma, and X-ray. You notice something here? The smaller it gets, the more powerful it gets. Here's primer number 1, well, no particular order, when it comes to field theory. Smaller the space, the higher capacitance. Could you repeat that after me? If you want to understand cosmic secrets of the universe, smaller the space, higher the capacitance. Something big should be a lot more powerful. Bigger explosion, bigger car engine, larger pistons, more water, like a Hoover Dam, as opposed to, well, it's just like one of those gigantic wind turbines that has a span of, what is it, like 600 feet or something, as opposed to like a backyard wind turbine which has a span of about 8 feet. Well, you have to think inverse to that. Smaller the space, higher the capacitance. Now, of course, there's no such thing as a photon. What we actually have here are rarefactions and then compressions. Rarefactions and then compressions. Rarefactions and then compressions. So right here we have the compressions. This is what modern quantum and relativity calls the photon. They are where there is a null point of electricity and magnetism. The loss of that capacitance is expressed in transverse, whether it's circular, linear polarization, transverse, electrical, and magnetic, right? So let's move on to magnetism, right? Because everything is one thing and one thing only. Energy, okay? However, human beings have things upside down and backwards. So before we explain the magnet here, how a much more powerful magnet has a much smaller field, we do understand now that the difference between low energetic EM, electromagnetism, and high energetic electromagnetism, right? Smaller space, higher the capacitance. This is a really small volume, right? This is a really huge volume, correct? So, the question that I keep getting asked is that someone will go on eBay and buy a neodymium iron boron, and now they're up to N55 Gauss, right? So, let's have two magnets here. Let's have this magnet, and let's have another magnet. Let's say it's the exact same size as a 1-inch cube magnet. Now, let's say this is an N40 Gauss, and this is an N50 Gauss over here, or N55, right? N55 Gauss right here, okay? N40 Gauss over here. Same size. Someone says, well, I'm going to buy one of those really, really powerful magnets. And then they buy it, and they've got their N40 Gauss. And I used to get this email all the time. And people say, well, you know, I noticed my N40 is pretty damn powerful. And it's really neat to mess with. And I said, well, I bought a much more expensive, it's not much more expensive, N55 Gauss. All the neodymium basically is coming out of China. And then they tell me, well, this N55 Gauss magnet is like this. Okay. They say, this magnet's a lot more powerful, but I noticed that the field doesn't extend out that far on the more powerful magnet. Now, you notice one thing here. If I hold this up, can you see that? You see the plane of inertia right there? There's a subdivision point right between. The magnet doesn't have two poles. It actually has the inverse of counter space. I've explained that in countless videos. Now, do you actually see that? Let me hold it so the light can see. There you go. I know you can see it. There's that white line right in the middle of the magnet, like the dividing line. That's the dielectric plane of inertia. If you're actually able to put two magnets together, or magnets actually have a hole in them, they have some oddball magnets like that, you stick a Gauss meter right in there. Move this light so it's not blinding. There we go. There we go. You'll notice there's no Gaussian flux. Okay, so how is it that the more powerful magnet has a much smaller, let me whip up my other magic marker here. You see, you won't read this in any science book anywhere because there's no branch of science that knows what a field is nor how magnetism works. Not one, because I own every book ever written on magnetism. Oh, you better believe me, I do. So we have this tiny field on the really powerful magnet, and we have this huge field on the slightly less powerful magnet. Yeah? About the neodymium iron boron, chromium, nickel plated. It's like, I got cheated. It's like, no, I actually bought that magnet from a guy that I know really well, like Emo Vendo or a couple other people. That really is an N55 Gauss. So, now here's the question before I answer it for you, and I basically already answered it when I was talking about light. Okay, let's throw up one waveform of light right here, or EM. Okay, huge spatial footprint. Low energy. Low energy. Kind of like this right here, huh? Low energy, right? Let's say that's infrared EM, right? Okay, so let's do a representation of, say, UV or something like that. A lot more powerful. A lot more powerful. This is IR, right? Infrared. This is UV, basically. You see this spatial footprint right here? You see this? Now this has a lot more power in EV volts than IR. I think it's like, what, 1.8 EV volts or 2 EV volts on UV? I can't remember. So, the question becomes is, can you put two and two together? Huge spatial footprint, low energy. Low spatial footprint, huge energy. Really powerful magnet, small magnetic field. Less powerful magnet, much larger magnetic field. Well, this doesn't make any more sense. A more powerful magnet should have a larger magnetic field. No, 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 no. This is where I tell you, you don't understand field theory, which is okay because nobody else understands it either. Smaller the space, the higher capacitance. Can you repeat after me? Smaller the space, higher the power, higher the capacitance. Smaller the space, higher the capacitance. I keep repeating myself for good reason, because I'm about to tell you something. Smaller the space, the higher the capacitance, right? Smaller the space, higher the capacitance. So this would be high power, this would be low power, right? Smaller the space, higher the capacitance. I'm repeating myself for a reason because I'm about to give you an answer here. Smaller the space, higher the capacitance. What am I really saying? Language is just concepts for human beings to discourse with each other. Smaller the space, the higher the capacitance. So what's the answer? This is much closer to counter space. This is much further away from counter space. Do you understand that? Smaller the space, the higher the capacitance. When I say smaller the space, what I'm saying is the greater the energy, the greater the inertia, the greater the acceleration. Space is only equal to the impotency of inertia and acceleration. Space is the inverse of energy. We think of energy as like explosions and big things. Things are expanding. Powerful. Bulldozers. You know what's really powerful? And this is an analogy. You know when something's really, really, really powerful? Well, you think, well, an atomic bomb explosion, that is a lot of energy. No, actually, that is the inverse of energy. That is impotency. That is the loss of energy. Do you know what something really powerful would be? It would be right about this size. Right about this size. Yeah, and spherical. That would be about 1.25 pounds of plutonium. Little silver ball. Little silver ball. Not much bigger than your testicle, depending on who you are. There's real power. The loss of that power is force and motion. Smaller the space, the higher the capacitance, the higher the power. Space equals force and motion equals magnetism. What you don't understand about a magnet, and nobody else does either generally because nobody knows anything about field theories. And once I get back to my question here again, that I've been asked so many times, I bought this really powerful magnet, but the field is smaller than my less powerful magnet. Right? This is an N55 Gauss. This is an N40 Gauss or an N35 Gauss magnet over here. Yeah, pretty big field. Fun to play with. What you don't understand is that the more powerful magnet, listen closely, has a smaller spatial footprint because it is more powerful. Power equals counter space. Smaller the space, higher the capacitance. This less powerful magnet has a bigger field. Space equals force and motion. What exists around the magnet, the field, is magnetism. When you increase the power of a magnet, you are increasing the power of inertia and acceleration at the plane of inertia. This is the secret you will not read about in any book on magnetism, any book on field theory, but it follows absolutely every observed phenomena of nature, of Mother Nature. Everything is exactly the same. Force and motion, inertia and acceleration. Everything is capacitance, resistance, permeability, and permittivity. Smaller the space, the higher the capacitance. The larger the space, the less the capacitance. Remember one thing. Space equals volume equals magnetism. Counter space equals inertia equals power. Really difficult, isn't it? It's not difficult at all. And these are the emails that I've been getting for many years. Why is the more powerful magnet have a more shallow magnetic field around it? Not as large of a volume of a magnetic field. This is the answer. This is the undeniable, irrefutable answer that you will see here first. You will see nowhere else. You will read nowhere else. This is one of many countless thousands of things that I will explain in the 4th, 5th, and 6th edition of my free book. You notice I said the word free, right? Uncovering the Missing Secrets of Magnetism. It literally is that simple. Because the most important thing that you don't have and nobody else has to understanding the secrets of the universe is one simple thing. Kind of like the Rosetta Stone. You remember the Rosetta Stone? We couldn't understand ancient Egyptian hieroglyphics. We still don't understand it, but we kind of understand them a little bit better. The Rosetta Stone, remember that? What we don't have is and I'm going to offer this to you, a primer. Without the primer, you have no ability to understand the secrets of the universe. You have to have a primer. Force and motion, inertia and acceleration, capacitance, resistance, permeability, permittivity. Everything is centrifugal divergence, centripetal convergence. Everything is pressure mediation. There is a one-page list, basically, without explanation. The explanation obviously comes in later pages, where you can get the entire primer of the secrets of the universe, because Mother Nature is that simple. Mother Nature does not work off unicorn particles, virtual particles, muons, gluons, gravitons, photons. These are arbitrary concepts thought up by the stupidity of humankind. Humanity is not evolved enough yet to understand these things. A few minds, like Tesla, have comprehended them. However, Tesla never wrote about this stuff. I love it when people tell me that. Like, well, you're not the first person to discover this. You know, Tesla did, or I was like, yeah, why don't you go find me where Nikola Tesla talks about this stuff? I love Nikola Tesla, not a lot, but he never discusses this stuff. This is the very simple answer of to why, and I get asked this question all the time. Why does a more powerful magnet have a smaller magnetic field? It's because the more powerful magnet natively will have a smaller magnetic field. Why? Because, listen closely, this is the ending of this video. Why? Let me ask the question again, and I'll answer it for you. Why does a more powerful magnet, which would be this one over this one, this would be N40 Gauss, more powerful magnet have a smaller magnetic field? Because power equals the dielectric. Magnetism equals impetancy, equals force and motion. What has more power? Smaller the space, the higher the capacitance. Capacitance is the dielectric, is the ether, is the inertia. Power is dielectric. Dielectric is CS, counter space. That is why the less powerful magnet, less power, more magnetic. When you have more magnetic, you have greater volume, because volume and magnetism are one and the exact same thing. The only difference is a turn of words in English. I say volume. Well, when you say volume, you say magnetism. When you say magnetism, you say volume. Repeat after me this 3 times. Volume is magnetism. Magnetism is volume. Volume is magnetism. Magnetism is volume. Volume is magnetism. Force and motion. Force is always divergent. What is divergent? Tell me what is divergent. Centrifugal divergence. That's where something is going out, right? What is divergent? This is divergent, right? This would not be divergent. This would be divergent. Pretty sure this is volume. Pretty sure this is also magnetism. This is centrifugal divergence. This is impetancy. This is the loss of power. This is why the less powerful magnet has a larger magnetic field. Because when you increase the power of a magnet, you decrease the volume of the magnetic field. There you go, folks. I hope you liked this video. You saw it here first. Absolutely here first, because this information exists Nowhere else. Mother Nature is that simple. Even an 8-year-old child could watch this video and understand it. I hope you like this video. I lead a simple life. If you want to make a small donation, that is always extremely appreciative. By the way, I'm going to give you an example. I took a donation that I got over the past week, and I bought, this is exactly what I bought, by the way. I bought 2 used Under Armour shirts off of eBay. Let me mention that they're used, okay? They're used shirts, okay? I bought a few groceries, and I was happy. I was happy to get 2 used shirts and a few groceries. I really appreciate that. I live simply. If anybody's seen my house, they know I live simply. I appreciate you for watching. More videos like this to come. Thank you so much. Lux e veritas. Let me actually write that one. Right here. I should remember that one. Lux e veritas. Thank you and goodbye.